Okay, so obviously I forgot to send Tony the title for my talk today. So it's Keynote by Ron Brightwell. Thanks, Tony, and Pori for inviting me to give this keynote. This is my, I think, third keynote at EuroMPI in the last 6 years. So I did 2017, 2019, 2022. So I have nothing more to say. This is a recap of things I've said before. If any of you heard those previous keynotes, you can read your email and surf the web and do all that kind of stuff, because I've got nothing new to say. When Tony invited me to give this talk, I reminded him that I have now been at Sandia for 27 years at the end of October. And for the first 13 of those, I was a staff member. And for the last 13 plus, I've been a manager. So as a manager, I don't do a whole lot of technical work anymore. I send and receive emails, I go to meetings, and I present other people's slides. And I have said this several times. And so what you're going to see in this talk is a whole bunch of other people's slides, and then a few of things that I throw in to stimulate thought and discussion and stuff like that. So hopefully I'm setting expectations for this talk. Anyway, let's get started. So the first thing I wanted to do, if I can advance the slides, let me see. Oh, there we go. So I wanted to say a few words about Rusty Lusk. So I didn't get a chance to contribute a video earlier, so I wanted to say a few words about Rusty. So I don't know how well you guys in the audience can see this, but Rusty was pretty influential early in my career. So when I was a grad student at Mississippi State way back when, in the 1994 timeframe, I think I first met Rusty and Bill. Gosh, it must have been at the Scalable Parallel Libraries conference that we had in Starkville. I had a very important role in that conference. I was the transportation engineer. So I picked people up at the Golden Triangle Airport and drove them to the hotels in downtown Starkville. And so I met some interesting people there. Dennis Gannon and Dan Reed and some other people I think were there. Bill and Rusty, I think that was the first time I met you guys. Later on, I actually did some technical work. So when I was porting MPI to the T3D, so there was a Cray T3D at NERSC when NERSC was back at Livermore. And Rusty had an account and I had an account. It was my advanced systems programming class project in the spring of 1995. I've told this story many times. I apologize for telling it again, but one of the things I did was we were porting MPI-CH to this machine. A few ports of MPI-CH existed. We were trying to show how well it worked. And the numbers I was getting from the T3D were better than what Cray was paying Edinburgh Parallel Computing Center to do for them. So EPCC had an implementation called CHIMP. Cray had paid them to port that to T3D. I was doing this as a school project, and my numbers were looking better than what Cray had paid for. And so Rusty was very excited. And as a grad student, I was trying to get an A in the class. That's all I was trying to do. And so when I was sending Rusty initial performance numbers, Rusty was very eager to get the code. And I was very eager not to share it because it was crap, right? I had to clean it all up. I wasn't thinking about checking it into MPI-CH and deploying it to other sites. I was thinking about getting it done and getting a grade. And so Rusty sent me an email, and I still have this email somewhere. I think it's on it's on tape. It's on a mini DV tape that I got off a Spark station. So if anybody has a mini DV tape reader that they could hook up to a Mac machine, I might be able to cover that email. But one of the first emails that Rusty sent to me as a grad student was telling me what a noble computer scientist I was because of the work that I was doing to port MPI-CH to the T3D. And so I was like, this is really cool. I just drove this guy to the airport. He's big, he's important, and he's telling me I'm doing good work. So it was very inspiring to me. This email I did manage to find, which is the fact that the approach that we took to MPI-CH on the T3D was also used for the SX4. So the lock-free queue mechanism that I actually did for that. So Rusty sent me this email, which I was able to recover, and basically said, hey, we used your idea for this port. And to me, that was awesome, right? Rusty was, for those of you that knew him well, one of the nicest guys you could ever know, right? Every time I saw him, I would talk to him. The last time I saw him was October of 2019 at a conference, at a workshop in Lyon. We were drinking wine and reminiscing and having a good time. So really fond memories of Rusty. And just as someone who was early in their career, to have someone like Rusty support you and encourage you was what I'll remember. All right. So since I have time, for those of you, this is Berkeley Mail, by the way. Do you know how you search for things in Berkeley Mail? You don't, right? Yeah, well, you use grep, and then you know what's there, and then you can't find it anyway. So I'm Zing and Z-minusing through all of my, anyway. For those of you that are as old as I am, you know what I mean. Okay, so goals for this talk. Analyze the current state of high-performance networking in MPI. Tell some stories. I think I've already accomplished that, but I'll probably tell some more. Ask some thought-provoking questions, maybe be controversial. The thing I like to do is overstate the impact of the portals, networking stuff that we've done on hardware, software, co-design. So, I think of portals as the thing I've been doing for the last whatever, and so it's hard not to talk about it. And then getting back to being a manager, which is reuse as many slides as possible, mine and others. And you'll see what I mean as we go along. Okay, so I stole this slide from Al Geis, and what it basically does is look at the progression of how we got to exascale. So exascale's here. I think Rajiv probably talked about this as well. We've been working in the DOE, the NNSA, and Oscar Office of Science for the last 6 years, 7 years, longer than that if you count when we actually started doing some exascale things. So I stole this from Al. This shows the progression of Oak Ridge machines that go from their machine Jaguar that broke the petaflops, was the second machine to get to a petaflops up to where we are now with Frontier. I was thinking that too. Can I? Maybe. If I knew how to use a Windows machine? No. Okay. See, I can't even use computers. I've been a manager so long. Maybe not how we expected it. So what I'm trying to set up here is I have a set of slides that go back and talk about the networking challenges of getting to exascale. And of course, most of them are wrong. So I just want to share with you how bad I am at predicting technologies that will get us to exascale. So the specifics of getting from Jaguar, the 2.3 petaflops machine, up to exascale performance. For those of you that were involved in exascale planning back in 2008, and looking at where we were going with, the DARPA study that was done, that Peter Kogi led, we had several challenges that were in front of us in getting to exascale. We had things like 2 swim lanes, we had lightweight cores, we had heavyweight cores, we didn't know how we were going to get there, we had multi-level memory, we had all these significant challenges. Resilience was talked about significantly because we were expecting the node count of these machines to be extremely large. And so what actually ended up happening? Well, it was more incremental than revolutionary in getting there. And so interesting things to point out here is that for a long time, we dealt with the challenge of multi-level memory. How are we going to deal with that? If you look at systems of today, it's not so much of an issue as we thought it was going to be, right? We still have multiple levels of memory, but we have abstractions that are actually managing those fairly well. Resilience, as I mentioned, didn't end up being as significant a problem as we thought it was going to be. The thing I'd like to point out, again, because I'm a portals guy, is that the Jaguar was using Cray-C Star, which was a portals-based interconnect back in that time frame, and we actually ended up at a Slingshot, which I'll talk a little bit more about as being a portals-based NIC as well. So transition to a story. So I was given a talk at ModSim, panel talk, which Martin's already heard, so he can stop paying attention. I don't know if anybody else is at ModSim. But there was a panel, and the panel question about exascale was, we've achieved exascale, but is it real? Is it a real machine? Does it run real codes? Does it do real things? And the challenge, the way people look at it is we're using graphics processing units to get to an exaflop, right? We're using something that, in 2008, we knew they were there, but we didn't know how central to exascale they would actually be. And so there's this question of, is this really a usable exascale machine? Because that was the DOE's goal for exascale, was to have a usable exascale machine. And it reminded me, because I'm older, of ASCII Red, the first teraflop system in 1996, that I basically went to Sandia to port MPI to. So I ported MPI-CH to ASCII Red. And at that time, when ASCII Red got to a teraflop, there were cynics throughout the HPC community because they had a hard time believing that we could use commodity processors to get to a teraflop. Because up until that point, most of the processors in large MPP machines had been special purpose, custom, floating point designed processors, right? And here we were using Intel Pentium 2s and Pentium Pros. And so there was this question of, are these really going to be able to achieve what we want them to from a teraflop's point of view? And so this discussion of, these are GPUs, these are commodity, these are things for video games, is that really what we want? Reminded me of this, wimpy little processors from commodity. Is this what we really want for teraflops? So it reminded me of this article, which I don't know if you guys can see at all, but this was a one-page article that was published in a journal. It was also in I can't remember where it was. It was like a one-page article that was posted somewhere, and then it ended up in one of the IEEE journals after that. But it was basically making fun of the teraflops machine and MPPs in general, and basically saying if you read it, it's a story of a mother and a daughter walking through a museum, and the thing that they stop and look at is a teraflops Rex, which was basically Intel teraflops machine, as being a dinosaur that nobody ever used. It was, and if you read some of these comments, it was basically hot air. It would never work. And the thing that was going to be most effective, according to this article, was large-scale SMPs. And so the only way to get to a real exaflop was with large-scale SMPs. The lesson here is commodity is always going to win. Commodity is always going to win, right? If I've learned anything in 27 years of doing this for high-performance computing, whatever is going to be mainstream, whatever is going to be commodity, that technology is largely going to win, right? It won for the teraflops versus large-scale SMPs. It's winning for GPUs as well. All right, so a couple of slides here on the interconnect for the Frontier machine. So Keith Underwood just gave a talk recently. It's Hot Interconnects, where he talked about the Cassini network interface for the Slingshot interconnect. So I had to steal some slides from Keith. So this is a set of slides from Keith. So this is basically Cray's story of doing exactly what I just said, which is making commodity win. This is their approach to taking commodity Ethernet technology and making it fit into HPC. Basically stealing the good parts of Ethernet and adding some special sauce within the constraints of what you can do with Ethernet to make a high performance interconnect. And so take a PHY that is largely used in the commodity space and make it work really well for HPC. And of course, part of this is libfabric, which is what they're basing everything on. I've done a lot of work in my career on network APIs. I sort of gave up on network APIs a long time ago because you can get enthralled with what the network API is, and I was more concerned with what the hardware actually does. The reason this slide is up there is because it has portals on it, because libfabric is based on portals. But the point of what we were doing with portals was to provide the semantics that you need to actually design hardware to do the right thing for MPI, right? And so it does all of these things listed there: one-sided operations, two-sided operations, including matching, and I'll talk more about that. Atomic operations, triggered operations, and locally managed offsets, which are a portals thing as well. So this is my Slingshot Cassini portals. This is cool because it's making the exascale machine work. So then he talks about how it's optimized for different things, MPI as well as PGAS. Again, the thing I like to point out here is progress. So progress is one of those things that I've talked about a lot in the past. One of the goals that we had for the portals design was to enable progress so that when you have non-blocking communications, the network traffic actually moves, that you take advantage of overlap and things like that as much as possible. So lots of work in Cassini to make that happen. The interesting thing here is that there are things in portals that you don't think about being there, but that enable scalability, like the fact that there's no persistent connections between the NICs, right? So this is something that we designed into portals to be connectionless as well, to try to push the scale boundaries so that you don't have this one-to-one correspondence between buffering and endpoints and things like that. And so, again, this slide is up here because the transport and implementation is inspired by Portals 4. So I'm just trying to drive home that message that, see, this is, let me get to it. Triggered operations. Again, another thing in Portals, what we stole from Quadrix, for those of you that know Quadrix ELAN and the way Quadrix worked, we stole triggered operations from that. We enhanced it a little bit to fit into the Portals model, but that stuff is there as well. We really designed triggered operations when we were thinking about them as a way to make collective operations go quickly, to basically get progress for collective operations. And so all that stuff is in there too for Cassini. Address translation, again, this is sort of one of the low-level details that you think about when you're doing NIC design. The only thing I want to drive home when I put up this slide is the fact that address translation is something that is important from a networking standpoint. The idea of dealing with virtual addresses and virtual memory when you're doing network communications can be a pain. Making sure that all your memory is locked down, making sure that when things move around, you know where they move around. Just the overhead of doing virtual address translation at the NIC layer, when you've got messages coming in at a very high rate, having to do translations and validations at the NIC level can actually be a significant overhead. When you've got messages coming in fairly quickly and you've got to make tens of nanoseconds decisions on where to put stuff, and you've got to do address translation and validation, that's something in the pipeline that can affect your performance and that you need to think about. Okay, so that's key slides on Cassini. The reason I put this slide up is because this is actually a slide that I presented at the keynote last time I gave it, I think in 2019, where I talked about, like I always do, Portals and its impact on networking technology, from the Intel Paragon to ASCII Red to Red Storm to the Cray XT, which is what Jaguar is, to the Atos machine, which is where the Bold BXI interconnect is based on Portals. And there's actually a Bold BXI V2, actually Atos BXI V2 coming out that's also still based on Portals. the thing, the reason I put this slide up is because the only thing I could say about Slingshot 3 years ago was that the Portals 4 header has support in Slingshot. And the only reason I could say that is because Steve Scott from Cray, who used to be at Cray, who was designing Slingshot, put that in a slide that he gave a talk, when he gave a talk. And that was the only thing I could say about Slingshot. So most of us who are in the DOE labs get roadmaps on where the vendors are going with their interconnect technology. So how long have I known about Slingshot? 6 years? 7 years? The only thing I could say about Slingshot and Portals was it supports the header. And so I would put this on a slide and people would say, why does Slingshot have support for a Portals header? And I'd say, you should ask Steve Scott that question. Because what I wanted to say is Slingshot is going to support Portals. But I couldn't really say that. The only thing I could say is what Steve said publicly. But Portals, it's interesting to look at because things like the triggered operations, one of the things that's happened with triggered operations, which we put in there again to optimize collective operations, the guys at AMD who were working on APUs, integrated CPUs and GPUs, looked at our triggered operations and said, this seems like a really good way to do GPU-initiated communications, right? Something we hadn't really intended to happen. We were only trying to optimize collective operations. They looked at those mechanisms and said, this is a really good way to separate data and control, right? You can initiate, you can set up a triggered operation, and as the GPU is computing kernels, it can then trigger and communication can move. And so there's a lot of work right now that is going on in the GPU community to try to make MPI and GPUs work better together by using some of these mechanisms. Okay, so this gets to the point where you should stop listening to me and paying any attention to me because I don't know what the hell I'm talking about. Because predictions are hard, especially about the future, right? So I was going back and looking at some of the slides. So I gave a talk in 2010 at a workshop at High PC. So this was in India. It was called the Workshop on Reaching Exascale in This Decade, which obviously we didn't do. So it was a unsuccessful workshop, except that it was the one time in the history of being at Sandia that I was allowed to fly business class. So if you want to hear more about that story, I can tell you. But it was my predictions for what we were going to be facing with high performance networking for exascale. And so I was focused on the network interface controller at that point, right? So I'm in the middle of doing Portals kinds of stuff. I've only been a manager for a year, so I still think I'm doing technical work. Power will be the #1 constraint for exascale systems. I think that's still true. I think the reason we went for GPUs is because of the power efficiency in terms of flops per watt. Al's got a whole set of slides on how flops per watt has changed. We're actually pretty efficient in terms of what exascale does with flops per watt for the Frontier system and probably the LCAP system that's going to deliver more. I tried to make the argument that the boundary, that the NIC was actually involved in being energy efficient, that as you're moving data, you can offload to the NIC and do things more efficiently there than just throwing everything up to the host processors and having the host processors do the computation. So take the things that are most power efficient. Reduce data movement. For example, if you're doing an all reduce, do all those operations on the NIC. You have fewer transfers to the host memory, fewer reads and writes on the host. Do them all at the network layer. So I was trying to make that argument. I think that's still true, but I think overall the percentage of power and energy that you have to deal with at the NIC level pales in comparison to what the memory subsystem and the processors do. So I was trying to make that point, but I don't know how well I did that. Trying to make the argument for specialized network hardware, and that you need to think about addressing in an address translation. So now you can see the reason I put up key slides on address translation is because I said that was going to be important in 2010. Okay, you guys are still sort of with me. All right. And then hardware support for active messages on arrival, right? So this was the thing that we were looking at with, it would be nice to be able to put a thread to sleep on a memory location when a message arrives, wake that thread up and have it go. And so very lightweight activation for making threads work. And we have some of that capability now. Applications must become more asynchronous. So this was the idea that exascale is going to have a lot of nodes. We're going to have 100,000 nodes. That didn't happen. What happened was we got a lot more computational power on the node from GPUs. And so if you look at the node count for the frontier system, it's actually around the 4,000 node range, right? So not a whole lot of network endpoints. A lot more computation at those endpoints, but the number of endpoints is not significant. And so I went into all of these things assuming that we're going to have a lot of network endpoints. I think some of these things are still important, but how important they are for exascale, I'm not sure. And then active messages, I think we're still trying to get to active message semantics. If you look at, there's some some more work recently on DPUs and SmartNICs where they're actually doing the actual active message thing where you bundle up a message that has the data and the computation in it, send it to the other side and run it. So you don't even have to have the computation at the remote destination. You send it along with the message. And DPUs and SmartNICs allow you to do that a little bit more effectively. And then runtime systems was the other thing we were worried about. Runtime systems, when we were thinking about it back then, it was MPI plus X, where X was threads, OpenMP or something like that. We didn't necessarily think about GPUs. And so it's interesting to go back and look at some of the thoughts we had when we weren't thinking about really GPUs as the main compute unit. Okay, so this was a panel at IEEE Cluster in 2011. And so this is the, we had several of these panels in the networking, HPC networking community, which were Ethernet versus Ethernet. When is Ethernet as a technology going to take over? When are proprietary interconnects going to go away? And so this was a panel along those lines. So here are the panel questions and my answers, which, are maybe right, maybe wrong. I don't know. Are commodity networks a lost cause? Yes. A balanced exascale system will require a non-commodity solution. Okay, well, if you look at Slingshot and what they've done with Ethernet, is it really Ethernet? The switches are capable of handling standard Ethernet, but you need the NICs to actually do the HPC Ethernet, right? And so this is sort of it is kind of a non-commodity solution, but it's based on a commodity technology. Well, the constraints of exascale require proprietary solutions. Power, performance, and resiliency requirements require tighter integration between network interface cores and memory. I think that's, for the most part, true. If you look at things that have been, the way GPUs became effective is when you really got a high-speed bus that connected the GPUs to the memory to the processor, right? So connecting things over an external I/O bus like PCI, not as efficient as getting something like NVLink and some of the other technologies. CXL is coming along doing the same thing. Can commodity networks sustain at exascale? Maybe. It depends on how much imbalance is tolerable. Again, I was looking at things like network bytes to flops ratio from the network to compute. We're still out of balance in terms of that, but that balance really doesn't impact the network that much. It basically means you can do whatever you want on the endpoints because the network communication is not really that affected by it. Will they be able to meet the stringent exascale requirements? No. I was pretty firm there. I guess I didn't have any other thoughts other than no. Will the non-HPC market ever require commoditization of proprietary exascale technologies? Yes. And so will the general purpose computing community, like, I don't know, hyperscalers, clouds, will they ever need that kind of capability? Yes, eventually. And so this is, if you look at what's been going on in the general purpose computing community, clouds, hyperscalers, they've been slowly adopting the networking technology that we've been developing in HPC for the last several years. I could say things like SmartNICs, but I've got slides later where I'll say that. right? They have done it in their own way by basically ignoring a lot of what the HPC networking community has been doing. So they picked up on things like, hey, it might be good to offload network functionality, right? It might be good to do that. It might be good to have a programmable network interface where you can actually take functions at the network level and optimize them. And so they've been doing that. And then the last one, will commodity networks eventually catch up with proprietary solutions? The technology push needed for exascale requires non-commodity solutions, but these technologies will accelerate commodity solutions for general purpose computing. So what I'm saying there is, I think it'll be interesting to see in the next handful of years what happens with technologies based on Ethernet like Slingshot. How much of an impact is this going to have on the community? What's going to happen with some of the hyperscalers when they see this technology? Is it something that they're going to try to adopt and leverage as well? By the way, I was hoping this would be much more of an interactive discussion, but I realize now with a hybrid meeting that that's really hard to do. So anyway, if you have any thoughts on any of this stuff, just let me know and we'll throw a mic at you and see. So I did talk about portals, of course, way back then. The thing that we focused on was high message rate, because that was something that we were worried about. Okay. What's going to drive the development of Portals 5? Okay. Can I wait till the end to answer that question? Because I actually had a slide on that I did include, but I'll talk about it at the end. So the thing I wanted to point out with this slide was that we were focused on flow control, and that doesn't matter. So I was trying to balance this with, yeah, I got some things right, but I got some things wrong. This was one of those things I got wrong. Flow control was the thing we were looking at with dealing with resource exhaustion at the endpoints, right? Whenever you have a hardware resource that you're trying to manage, the thing you have to think about managing with the hardware resource is what happens when you run out of that resource. How do you manage that resource with software? How do you fail over? And so we did work in Portals to do that. I still think this is one of the things that's under the covers that doesn't get a lot of attention. And it's important, but it's not something that was really any kind of critical capability for exascale. And then I argued that we need a hardware implementation that's designed for intelligent and programmable NICs. So I think we got there. Argued that we needed new functionality for doing one-sided operations. Scalable event delivery was one of the things that we actually looked at pretty hard. And I think we've gotten some of that, not only in Portals, but in other network APIs as well. If you look at things that are going on in UCX and other low-level networking layers, that became important. Knowing when a one-sided operation has completed at the target and how to recognize that through some lightweight mechanism. And then, of course, we were looking at triggers, and I talked about that already. So from my perspective, it only took about 17 years to actually get what we want, right? So this is the ranting part of my, I'm a grumpy old man now. The first paper that we wrote on how to do a hardware unit for MPI matching for NIC offload. This is a 2005 IPDPS paper. And so it was basically me and Keith Underwood going, if IXP processors can do, that Intel designed to do networking translations in their switches, can do ternary operations, why can't we do matching? Why can't we design something to do matching? Shouldn't be that hard, right? Should be fairly straightforward. And so Keith and I came up with an approach for doing that. We had a group of hardware guys at Sandia. So Scott Hemmert, who is an FPGA expert, Aaron Rodriguez, who's a network simulation guy. Aaron just left to go to Samsung. And then Rich Murphy. Rich Murphy was a memory processor guy at Sandia, who eventually went to Micron and is now at his own company. But we designed this hardware unit. We simulated it using a precursor to the structural simulation toolkit at Sandia. And simulated it, got results from it. We had Scott, who's our FPGA guy, coded up in an FPGA to see what timings would make sense. And it was doable and it was effective, right? And so this was out there in 2005. And basically Keith took that idea with him when he left Sandia and went to Intel, eventually ended up at Cray. I'm not going to say this hardware unit is actually what's in Slingshot, what's in Cassini. It's probably close to that, but I don't care. It was something that we worked on 17 years ago that actually made it into hardware in some shape or form. And so the interesting thing about this is, and I could tell long stories about this, is the way it ended up where it is, right? It wasn't because the science was good. It wasn't because the technology was good. There were so many other factors that were involved in taking something like this from a research perspective and actually seeing it realized in product. That doesn't really happen very often in my career, in my experience. I think it's going to happen more often because of the way hardware design is evolving. It's getting a lot easier to prototype and do things in hardware. And I think there are a lot more opportunities for that. But there's a whole host of reasons why we were able to be successful with this. And while I like to take credit for it, I can't, because if you look at some of the things that happened along the way, just for example, the original thing Keith started working on was actually supposed to be part of Intel Knight's Landing line processors, right? Those don't exist anymore, right? And so Keith put a significant amount of effort into designing a hardware component for several years of his life that then got killed, right? And so for a while we were looking at this saying, oh, we're going to get something close to what we wanted. And then Intel makes a decision and it all goes away, right? And then somebody else makes a decision and some of it comes back. So it's just been an interesting experience to do that. So what I want to talk about here is progress. And I mentioned this already. So the thing that I started out looking at early in my career was the impact of progress. And what we were trying to do is make sure, again, when I implemented MPI on ASCII Red, we had progress, right? This is one of the things that was missing from the MPI implementation on the Cray T3D, right? Because of the way the T3D worked, because of the way SHMEM on the T3D worked, you couldn't get progress, you couldn't get overlap, you couldn't get some of those things. And so when I implemented MPI on ASCII Red, and you could actually see the benefit of doing that, it made sense to try to figure out how to get progress. And so, you can talk about latency, you can talk about bandwidth and message rate and all the sort of performance aspects of MPI and how to get it. But one of the things that we kind of focused on was progress. And in fact, when we looked at the other networking technologies that were out there, it wasn't clear how we were going to get progress if we put MPI on top of them. And so I would go have these discussions with vendors about, their network API and the challenges of getting progress for MPI from their network API. And again, these are stories, right? But it was always the same when you go talk to the MirrorNet guys. GM is perfect, right? You can put anything on top of GM and it'll work fine. You can get progress, you just need another thread, it's fine. And so GM was fine until MX came out. And then MirrorNet said, you should use MX. And was like, well, what was wrong with GM? Because I've been trying to figure that out. And I'll pick on the InfiniBand guys the same way. We used to talk about InfiniBand and say, verbs don't give you what you want. You want something different. Verbs is fine, works everywhere, it's fine, until it doesn't. And then UCX is what you really need, right? So there's always this challenge of really demonstrating what's important and trying to convince vendors to do the right thing. Again, lots of ways to get progress, but NICA offload was an obvious choice. Get the hardware to do what we want it to do. This associative list processing unit was pretty effective at doing that. And we wanted, the triggered operations were really a way to get progress for collectives. Because if you want progress for point to point, you should want progress for collectives as well. And so it's what can we do from a NIC layer, what can we do from a NIC API to actually get progress for collective operations? And going back to what projects have done with triggered operations made a whole lot of sense. And again, a lot of that stuff is actually being leveraged by GPUs now. So anyway, the whole point of this is that when I stopped thinking about portals as a network API and started thinking about it as a tool for co-design, we were actually able to have some significant influence. And so people still ask me this. In fact, Matt Leininger asked me this the other day. What do you think about UCX? It's not portals. And I said, I don't care. The point of this was to get the right functionality from the hardware, right? If your network hardware is giving you the things that you need to get scalability and performance for MPI, I don't care what API. It could be sockets. It could be whatever. I just don't want us to continually have to do this mismatch, fix this mismatch of layers between what the application semantics need and what the network hardware provides you, right? That's the only thing I'm trying to do. Okay, so I think this is the 2019 talk I gave on meeting future needs of HPC with MPI. This is, again, a rant of my experience in dealing with economics. So I never thought when I went into high performance computing and computer science that everything I do is driven by economics. For those students in the room, you should know that everything that you do as a computer scientist, if you do anything in high performance computing, it's driven by economics. So don't forget that. Again, I can tell stories, but this was, a significant amount of my career. And again, Martin's heard me complain about this already in the past couple of months. So I apologize to Martin again. Significant amount of my career trying to argue with vendors that programmable NICs actually make sense, right? And every time I talked to them, it was, it was not viable. Either there was a technical solution that was just as good. So, you can't do programmable NICs. Look, this is the reason why Miracom and Quadrix went out of business, because they tried to have their custom silicon for doing programmable NICs. There's no market for it. It's HPC, and so you get a broader market. Nobody cares. It's easy to dedicate cores, as long as those cores don't slow down. And then the cores slowed down. And so they had to come up with other arguments why it made sense. Even Cray had to do things like core specialization, which is to dedicate host cores to doing network functionality, right? Every argument I could come up with, technical, on why it made sense to do programmable NICs, the vendors would shoot down in some way, shape, or form, with either an alternative technical solution or with an economic argument of it not being viable. This is my point, right? So every argument I was making to them didn't matter until it did matter, right? And so what happened is the cloud computing community that was trying to use host processors and sell them to everybody was having this issue because most of the virtualized network functions that they were doing they had to run all their networking stuff on the host, right? And people were paying for host cycles and not getting all of them, because a significant amount of those host cycles were being run to handle virtualization functionality at the network level. And they said, this is not good when you're having people pay for host processors and they're actually not getting them because you're too busy running other networking functionality. How should we handle that? I know. Let's put some processors down on the network interface and do the network virtualization and network processing functions in the network. And so we went from, this is not viable, it doesn't make sense, there's a whole bunch of other ways to do this, to, hey, this is cool, you guys should use these, right? And so this is why I said economics, right? It wasn't a technical argument that made the difference. It was a significant other community saying, we need this capability. And then the vendors were able to actually go on and provide it. Right, good. There's a question on energy consumption for smart NICs. I'll get to that. Remind me if I don't get to that. So I actually focused a couple of slides in this talk 3 years ago on what I thought cloud and enterprise were going to do in terms of networking capability. And so most of this it's interesting because I'm not sure how much of this has actually happened. Some of it has, but the point of this is that I think there's a convergence now of what's going on in the cloud community and hyperscalers with what's going on in HPC. A lot of the network functionality that we've become accustomed to and designed to, they're actually starting to adopt. And so I think there are things that this community is looking at. For example, Ethernet physical layer may actually work for HPC with the right tweaks, right? So I think that's happening with Slingshot. The cost of hardware-based virtualization capabilities is acceptable. I think virtualization is one of those things that's going to be seen in HPC a lot more. I mean, we have container technology now, which is OS virtualization. I think the cost of doing virtual machines and containers is going to continue to be minimal for HPC, and that it's going to allow us to adopt a lot more of the technologies that other community has been working on for a long time. I also think fewer HPC application developers really care about high performance. If you look at what's going on in the community now, there's this integration of AI and ML into their workflows, more advanced workflows. And so the high performance MPI modeling and simulation part of the workflow is only one aspect of it. But I think it's going to encapsulate a whole lot more of that. High level languages and DSLs can be effective. You know, if you look at things like the Cocos layer that Sandia has developed for GPUs, I think a lot of people are, you know, there's application uptake of that has been significant in the community. Okay, SmartNICs DPUs. So people are using these like crazy now because, you know, they're giving people what they want. We're figuring out, hey, we can do application offload on them as well. So even if we can't, from a high performance computing perspective, do things with the networking layer, we're not constrained by that. We can actually offload to the application. So there's all kinds of work now. There was a Georgia Tech Sandia paper at IPDPS that was a best paper nominee on optimizing MD by offloading parts of the MD calculations to SmartNICs. So not using them to do actual networking stuff, but using them to do application stuff. Project at Sandia and other places probably offloading IO services to DPUs, right? So what can you do from a data processing point of view to offload IO and things like that? You can expect lots of papers from people on offloading MPI operations to SmartNICs and DPUs, right? We see this with every new generation of programmable and network offload things. Let's go make things more efficient. You know, look at all the things in MPI that we need processing for. Offloading data type processing, perhaps, to DPUs and things like that. What else are they good for? This argument on edge computing I hear all the time, right? And so this goes to energy efficiency, right? This is the edge is going to have to process data and do data reduction more efficiently because you don't want to send all the data back to some centralized location in the cloud or an HPC server to do data reduction. So they're designed to do edge computing. I still don't understand the energy efficiency arguments of that, because in my mind, you're taking a DPU that's got a whole bunch of cores and a whole bunch of memory and putting it someplace where you're power constrained. And I'm still trying to understand the energy argument there, because the network interface is the thing that is always on. It's always on, and I would love to hear more about that from somebody. And then there's a whole bunch of work in the AI ML to take advantage of DPUs for training and things like that. But that's a space that I think is evolving. The interesting thing with SmartNICs and DPUs is they don't seem to address the MPI GPU performance challenges, right? So it's been interesting watching NVIDIA and Mellanox go down this road of, you know, the things that we're interested in, making GPUs work really well for an MPI application on something like Frontier and LCAP, to DPUs. And SmartNICs designed for an AI ML cloud computing hyperscaler community, because I'm not sure any of the things that we care about from making MPI go fast on GPUs is actually solved by doing DPUs at all. I've had discussions with NVIDIA folks on that, and I think those are going down two separate paths. It would be nice if they figured out how to come together to make things work more effectively. And then what's the programming model? Everybody wants to figure out ways to offload parts of their application or parts of their libraries and services. There's work going on in the UCF on OpenSnappy, which is trying to figure out how we can actually have a programming system programming environment for DPUs. And then things like CXL, which is, you know, are we going to have the ability to put a whole bunch of different SoCs on a package where you have NIC functionality, memory, processors, accelerators, all on an internal fabric that's high performance, low latency, and memory coherent, right? What's that going to do for processing? And then some final thoughts here. Slingshot seems to achieve HPC network performance with Ethernet. What does this mean for InfiniBand? Again, we've seen in the past where proprietary technologies don't survive long when they're up against commodity technologies, right? What's going to happen in this space? We've still got basically at a PHY level, NVIDIA Mellanox, Cornelis networks, and BXI V2 that are dependent on that. Is that going to be a large enough community for a proprietary fabric, proprietary PHY to actually keep it going? What's the uptake of the adoption of something like a high performance Ethernet going to look like? And then this is my controversial maybe slide. HPC is dead. So if you look at it from the perspective of all of the things that we're looking at with integration of hyperscalers, cloud computing, virtualization technologies, AI, ML, where does HPC fit into that? You can make an argument that future HPC systems are not really HPC systems, or whatever the commodity vendors are designing for these other markets, and we're trying to take advantage of them, right? And the more that market and those people start to adopt our core technologies like deep, high performance networking, the more we're going to start to look like them, and the less we're going to be specific to something HPC cares about. So the way I think about this is we're not going to have HPC systems in the future. They're going to be, designed for other communities, other problems, and we're going to try to leverage them as much as possible. The way some people say this is HPC is now ubiquitous, right? The technologies that we care about are all being adopted by those other markets. And so whereas I look at it as HPC is dead, everybody else or others look at it as, well, that just means HPC is everywhere, right? It hasn't really died. It's just made its way into other places. I guess it depends on if you're half full, half empty kind of guy. Interestingly enough, I don't think there are any HPC vendors anymore, right? People who are really focused on HPC, they used to want to give lip service to the HPC community for, roadmaps. They would talk to us about their technology because they wanted us to buy their systems. They wanted us to buy their hardware. More and more, they don't want to sell us hardware. They don't even want to tell us what they're doing. They want to keep that information more close to their vest because they want us to lease time on their machines, right? They're looking at a cloud model, right? It is entirely possible that in the next 5 to 10 years, we're just going to be getting cycles on Amazon for running all of our HPC workloads, right? That is potentially possible. And then when I've tried to think about what is it that uniquely identifies HPC, right? So 27 years ago, I was pretty confident of what made it an HPC system. When I think about systems today, and I think about what makes it an HPC system, the thing I keep coming back to is it runs MPI. You have MPI apps you need to run. In fact, when you talk to people in the applications community about their complex workflows, I mean, they talk about the HPC aspect of it. It's just the MPI application, right? MPI is sort of now that thing that uniquely identifies HPC. And I think that's an interesting perspective. Okay, so that was my last slide. These are people I stole slides from. So thank you. How do I see them? Okay, so concerns, trends, challenges drive the development of Portals 5. So this is, we've had lots of discussions. Whit Schoenbein is the guy at Sandia who's actually been running the Portals meetings lately. And we've been talking with people like Torsten, who were involved in some, Torsten Heffler, who was involved in doing some Portals 4 stuff. And we have a list of things that we'd like to look at for Portals 5. What kind of challenges are we looking at? The basic thing we're looking at is how, if you look at the spin work that we did with Torsten, it was trying to understand the technology drivers for programmable NICs, right? What capabilities are NICs going to have in the future? And how do we expose that in a way that makes sense? And that's really challenging because it's almost like you're looking at a piece of hardware and you want something that's portable, right? So we designed to some abstract things when we did spin, and we don't want to constrain what the hardware would look like, right? We're doing co-design. We're trying to figure out from a hardware perspective, how are programmable NICs and DPUs evolving to what kind of capabilities do we need from an application perspective to actually drive this. So I know I'm not really answering this question very well, but it's the key things I think that are changing the way we look at designing NICs is this co-design aspect of it. And the fact that we're relying on simulation environments more and more to do this kind of thing. Because we have the ability to impact hardware more easily than we did 25 years ago, we can actually do hardware design more easily. But specifically what we're trying to do is figure out from an application perspective what makes the most sense. And we're rethinking a lot of what we did for portals. Again, this is general hand-wavy stuff because it's really hard to talk about the specifics of what's driving portals. Curious how you see power concerns influencing the adoption of smart NIC, given smart NICs that consume significantly more power than a traditional NIC. Right. So this is exactly what I said. I'm still trying to understand the power energy argument of smart NICs because the more processing power, the more memory you put on a smart NIC, unless you're really taking advantage of that in some significant way, I think you're using more power than you were before. And so I can't make a power energy argument for smart NICs at this point. And I've heard people say that, like, when I hear these edge computing talks, it sounds really cool. And then when we start looking at the numbers, I'm not sure it actually adds up. Yes. Yes. Yeah. So I think there's an argument to be made there. I don't see it, right? So I don't see the efficiencies, right? I made this argument that reducing the amount of memory that you send over the bus, right? So if you have a network interface on the other end of a PCI bus, okay, I get that. When you're looking at a node that has CXL on it, right, where everything is sort of interconnected by CXL, I'm not sure you're saving anything by doing that, right? Again, I'm not a hardware guy, so maybe there's a significant energy, power energy performance win there. I just don't see it. An extension of the above question in the context of progress discussion, how do you see power concerns influencing the viability of on-load to the CPU? Energy per bit of CPU cores handling communication versus a dedicated ASIC or smart NIC. Does this predict a technology trend for YATA scale? So this is one of the things that I think is really interesting about node design, right? So I talked about CXL, I talked about coherency. There used to be a path for integrated network interfaces, right? So putting the network interface right on the memory bus. In fact, this was the way the world was 30 years ago when I started in HPC. Interconnect performance was paramount, and so it was on the memory bus. We've transitioned away from that to something commodity, and we're slowly working our way back towards it now. But I think it changes the whole power energy consumption arguments become different when you start looking at, is a network interface on a CXL on a node, is that an integrated NIC, right? Is it coherent? Do we still think of that as an integrated NIC, or is it still something that's discrete? In fact, one of the discussions we've been having along the lines of Portals 5 is, suppose we have other accelerators, right? So we have GPUs, we have CPUs, we have some other accelerators because there's a significant amount of accelerator technology being developed. What's the component, in each of those accelerators that will give you the network capability that you need, right? So we're already looking at things like, what do GPUs need to make MPI go fast? What kinds of triggered operations do they need? With other accelerators, is there a component of the network that has to sit on those to make them work as effectively as well, right? Or, a lot of people have thought when they think about networking, they think about the processor as the endpoint or the GPU as the endpoint. And we've always thought about memory is the endpoint, right? So this separation of control and data, right? Triggered operations or control, those are different from transfers into memory. But thinking about, what's the aspect of the network that has to go into these accelerators to actually give it the capability that you need is an interesting discussion. I don't know if that got to the question or not. And then Jim Dinan, do you see virtual clusters model discussed at ALPS at CSCS as a trend that will catch on across HPC centers? How, if at all, would SmartNICs play a role? So I didn't see the virtual clusters model discussion for ALPS, but I think virtualization is. I had a slide that had technologies that I think are going to influence network design and our ability to adopt what's going on in the broader hyperscaler community in HPC. Virtualization is certainly one of those. I think I mentioned security is the other one, right? There's a lot of zero trust work going on that's out in the community, and I think that's going to impact us as well, especially in places like the DOE, where the government tends to see things like zero trust and say, oh yeah, that's good, we want that, and we're going to have to figure out what to do with it from an HPC context, because people are going to tell us, they're not going to give us the option. They're going to say, we like that security of the zero trust model. You guys now have to figure out how to actually deploy it and use it in HPC systems. And so there's interesting aspects of security that we may have to deal with, and networking is one of those places that's going to be affected. So I waved my hands at the answer to that question as well. Okay, I think that's what's in chats. Yeah, what's in the chat. Anything else? Thanks, Bronis.